right, good evening, everybody. Thank you for being here tonight. Not too bad a crowd for given it's June. Usually we have smaller crowds over the summer because everybody, of course, is on vacation and whatnot. So anyway, nice to see you all here. And it's air conditioned in here, which is always a plus, given the temperature outside. So anyway, let's go ahead and get going here. A couple things. We are going to run the bidding on the telescopes through the next break. And at the end of the break, if we've gotten bids, we'll see who gets what. If you are interested in a telescope, they do have some information about them on the wall, but you really want to check with James right here. Because James is the guy who checked them all out and for functionality and what they can and can't do and whatever. So before you pay us any money, make sure you talk to James first is the idea. So anyway, welcome to everybody. Let's go ahead and get going. We have a fairly full evening tonight. We've got two presentations. We actually got one from James. And has anybody seen Lavi here? It's interesting. Okay, we have a member presentation from a young gentleman named Lavi, but I don't see him here yet. So hopefully he'll arrive. Anyway, okay. First of all, welcome to those here in the room. Thank you to those here on Zoom as welcome as well. As always, we always say this, as always, we hope you enjoy yourselves tonight. We hope you learn something interesting while you're here. We hope you make a new friend, and we hope you connect with old friends as well. So thank you for being here all. Always we ask, is there any visitors here tonight? People who've never been here before? We have one here. So we're nothing embarrassing here. You can see it on the slide there, just your name and a little bit about, just run through the list.
My name is Jason Hutt. I used to be a member years ago and just got out of it. And then I just recently bought a 8-inch SCT. So I want to get back into astronomy. And basically I found you online.
Okay. All right. Well, welcome back. Yes, thank you for being here. Anybody else? Any other hands? I think I only saw one, but all right, let's continue on. Thank you for being here tonight. We appreciate that. Tonight's agenda is going to be a little bit different than what you see up here. We have a few basic announcements. We do them every meeting. It takes like 5 minutes, so we'll do those announcements. We did have 2 member presentations scheduled, but one of the people is not here. So we'll probably just have James Yoder talking a little bit about how to use AstroPlanner. So that'll be a presentation coming up later. Then we have a 7th inning stretch. We'll have continue. You can look at telescopes and offer a bid if you'd like to. You also want to check out our webpage, James's webpage. He does on behalf of the club, because we have a ton of eyepieces on that site now. The gentleman who left us, who passed on, he had a whole bunch of bino viewers. He actually had 5 different bino viewers, and he had double eyepieces for all of them. So we have, I don't know, what is it, maybe 60, 70 some eyepieces we have available as well. So that's all on James's website. So I'll be mentioning that website here in just a little bit in the announcements, but you want to check that out as well. Some of the telescope or some of the eyepieces are, kind of standard Plossl kind of stuff, but he has a lot of televiews and other really nice eyepieces as well. So you want to definitely check that out. After our break, our main presentation tonight will be from Tom, who's up here at the front table, and Rick, who's in the front row right here. They've been working on a project, as you can see there, from the intensity interferometer. And so they'll talk a little bit about this project they've been working on for us. So there's our agenda for tonight. General announcements. This takes about 5 minutes. We do it every meeting. So some of you have probably seen this before. So if you want to join the club or renew your membership, at least 3 ways to do this. This is from our website. You can do it online through PayPal and just filling out some online forms. You can do it through mail. And I've added a few things in red up there about how to do that via mail. Or you can go ahead and you can do that in person. Against the back wall back there is Brooks. And Brooks is our treasurer, and he can get you signed up or renew your membership or whatever you'd like to do. Notice there is a new member guide button there, kind of off on the right-hand side of the screen. If you click that, it does bring up a little PDF, tells you a little bit about what a member means. As you saw tonight, we are actually starting to do a little bit more of, if we get telescopes or telescope equipment come in or things like that, we are going to start offering it to members first for a short period of time, and then we're going to go ahead and offer it to the general public as well. So it's one of those things, what was it, American Express or MasterCard, almost membership have its privileges or whatever. So we're going to kind of follow that a little bit. So anyway, just be aware of that going forward. If you would like to know what's happening here at EVAC, it says 3 ways. There's actually a 4th way I'm going to mention verbally. But on our website, you can always go out to our homepage and click on the subscribe link and get onto our mailing list. You'll get probably half a dozen emails a month. We don't sell the list to anybody. You're not going to get spammed by every astronomical group on the country because we sell your email address off or whatever. So you can subscribe to that, and anything coming up, typically we announce there. What's not up on the slides is we also have a Facebook page. I'll probably add this to the slides a little bit later for next month. But we also are starting to announce things quite a bit on our Facebook page as well, since a lot of people seem to look at that. We also have out on our website an events and meetings page, and so you can always check the calendar there. For instance, Thursday, there was an event out in Santan, a big group out there, about 100 people. And I think 3 people from the group here were out there with their telescopes, kind of showing people the sky. And apparently it was a fun night, really crazy with about 100 people there, but they had a good time and it was fun. So anyway, this is kind of the slow time of year for some of the events, but come September when the weather gets a little bit cooler and the nights get a little bit longer, which helps as well, we actually do a lot more public stuff, and you'll see a lot more on this calendar towards the fall. There's also a newsletter that comes out once a month, and so you can always check that out to see what's going on, and typically anything that's coming up, we kind of mention on the newsletter as well. If you would like equipment, well, there you go. There's 3 right over there. But in addition to that, we have out on our webpage a couple of links. You can see used equipment for sale and equipment for rent. So if you'd like to buy something, James actually runs, James over here, James runs that website where it's equipment for sale and equipment for rent. And he has tons of stuff out there. And like I said, we just had a whole bunch of stuff come in over the last few months from the gentleman who passed on. And so all that equipment's out there, and some of it's pretty nice. And we regularly get equipment. I just got another email this morning from another guy who wants to donate his telescope. He says it's great shape. He just doesn't use it. So why set it around the house? So he's donating it to us. So that'll be on the website here soon as well. Also equipment for rent. We have a variety of things out there. We have a variety of telescopes. We even have one of the new C-Star electronic telescopes you can rent and try it out if you'd like to see how it works, and then maybe purchase one for yourself. We also have astrophotography, little setup for rent. So if you'd like to try out some astrophotography, we have a setup you can rent for a few weeks to a month or whatever, and try that out also. So we have quite a bit of rental gear available for you out there. If you would like to learn more, out on our website, you can click this page here, the news and resources page, and there is a virtual beginners lab there. You can see some of the blue boxes on the web page there. There's actually 33 of those if you look down the whole page. And if you click on any one of those, it brings up a little blurb that tells you more about that particular topic. So it's just a way of learning if you'd like to. Once again, one of our charters as a group is to give back to the community, educate the community, get the community interested in space and astronomy and all those things that are related to that. So one of the ways we do this is, of course, we have the observatory over here, and we are open to the public every Friday and Saturday night. So if you'd like to become a telescope operator, volunteer once a month or a few times a year or whatever that might be, go ahead and sign up for that. The information's there on the slide, as you can see. And you can help with the public. Once again, it's a little hot this time of year. The nights are pretty short, so we're not out there very long right now. But, come once again, September, the nights are longer, it's cooler. We get a lot more people over there. In fact, a lot of times we'll see maybe upwards of 150, 200 people some nights over there at the observatory. So it's pretty busy. And it's actually a lot of fun to go out there, and people are very interested, and you can show them pretty much anything and they're fascinated by it. So it's a fun thing to do. In addition to that, we also have private star parties that we offer for HOAs, science centers, community groups, whatever, schools, so forth. Once again, we had one just this Thursday night, a couple of nights ago, actually yesterday. This is only Friday, isn't it? You can tell I had a busy week, right? Thursday feels like last week already, and it was only yesterday. So anyway, you can get involved in those, and there is a place you can sign up for the mailing list if you'd like to maybe volunteer some time there. Most of these events are about 2 hours long, and so with travel time and setup and tear down time, it's about a 3-hour evening for you is what it is. And it's a lot of fun. I would highly recommend if you want to do that. So anyway, be aware of that. Member presentations is what we have. And Lavi, is Lavi? Ah, you are here. Perfect. So great. We have two member presentations tonight. One is from Lavi, one is from James. And you are on, sir. If you want to come on up, it's come on up. You're all set to go. So this is Lavi Berko, and he is going to be talking to us a little bit about the physics of space travel. A nice short little presentation. It's very nice. I looked at the slides earlier this morning, and nice job. So I'm impressed. So here's your microphone.
Thank you.
And just up or down or back and forth, whichever way you want to go. And
Hi, my name is Lavi, and I'm going to talk about the physics of space travel. Efficiency is the #1 priority when it comes to space travel. Oh, I guess schemas can be important too. Math is one of the best tools for rocket physics, and it helps a lot when it comes with efficiency. The first step is to leave Earth's surface. To start an interstellar journey, you need to leave the Earth. After all, if you can't get the car out of the driveway, you can't go anywhere. This equation over here is used to calculate the escape velocity, or the speed necessary to escape the gravitational field of a planet. In this equation, G is the universal gravitational constant, M is the mass of a planet, and R is the radius plus the height from the planet's surface. In order to go somewhere, you gotta leave something behind, TARS. You may remember that quote from the Interstellar movie. There is an equation in rocket physics known as the rocket equation, which is used to calculate the change in velocity of a spacecraft. In this equation, V is the velocity that the fuel moves relative to the ship, and it is known as the exit velocity. Mi is the mass of the spacecraft without the fuel, or the initial mass. Mf is the empty or final mass, which is the mass of the spacecraft without the fuel. The biggest problem with rockets is that they need to use fuel, and fuel has mass. And as you can see in this equation, mass plays a role in acceleration. Plus mass means weight. Modern space travel is not just rockets. Ion thrusters are a very hot topic in space exploration. An ion thruster takes neutral gas and strips off its electrons, turning them into ions. These ions then get accelerated by magnetic fields inside the thruster, where they then exit. The simple reason that this accelerates the spacecraft can be explained with Newton's third law, or the quote from TARS. Ion thrusters have been used by satellites in spacecraft for decades, and because they are efficient for all sorts of maneuvers. The next step after escaping the Earth is to escape the solar system. But how do we do that? It's pretty tricky for us as it is to escape the Earth, and the solar system's escape velocity is over 4 times that of the Earth's. Well, so what do you do? Well, lucky for us, we have a tool in our stellar backyard, the planets. We can launch a rocket to a trajectory where it goes to close proximity to a planet. At a close proximity, it can steal some of the planet's gravitational potential energy. The gravitational potential energy gets converted into a kinetic energy, which is translated into an increase in velocity. Gravitational slingshots can be used to speed up, slow down, or even change the direction of travel of a spacecraft, making them extremely useful for maneuvers throughout the solar system. There are two types of gravitational slingshots, powered and unpowered. Powered gravitational slingshots increase the velocity under the power of the spacecraft. This equation over here is used to calculate the change in velocity of the spacecraft, depending on the velocity of the planet and the cosine of the angle that the spacecraft is relative to the planet. Science fiction space travel can be pretty bizarre, but real ideas can be even crazier. Project Orion was a concept that used nuclear bombs as a source of power. Project Orion launched nuclear bombs into space where they would then explode. The explosions would then push a pusher plate, which would accelerate the spacecraft. Theoretically, it would go up to 10% of the speed of light, but it never happened due to the nuclear space treaty in the 1960s. Despite that, tests have proven the concept. Oh, you may also recognize a similar spacecraft in the Netflix series Three-Body Problem. In science fiction movies, there are two types of space travel that appear a lot. Wormholes and hyperdrives are based on real physics. So how do they work? Well, wormholes are like tunnels through space-time, which can act as shortcuts. Hyperdrives warp the space-time around the spacecraft. And basically, hyperdrives or warp drives pull space-time behind it, which accelerates it faster and faster. Theoretically, it could go from one side of the universe to the other in a snap. Unfortunately for us, these concepts are very, very far in the future, and they are way beyond our capabilities. When it comes to going near the speed of light, some very strange things happen. According to a paper by Tom, hi Tom, some problems with communication could appear. When it comes in light-based communication, relativistic effects such as time dilation may appear due to inertial timeframes or the internal relative clocks. This could cause problems with delays in messages. So far, the concepts that I have talked about are most likely to happen in the very, very far future. But there is one idea, light sails, that will happen in the near future. Light sails use the power of light as a source of propulsion. Light, even though it is massless, still provides a small force, and a small force combined with a large surface area can lead to very high accelerations. Theoretically, they can go up to half of the speed of light. There is a mission concept, Breakthrough Starshot, which plans to send a large fleet of light sails to the nearest star after our sun, Proxima Centauri. This fleet of hundreds of light sails will be powered by lasers and will theoretically go up to 20% of the speed of light. At 20% of the speed of light, it will take slightly over 20 years to arrive to Proxima Centauri. Though 20 years may seem like a long time, compared to the 70,000 with conventional rocket methods, it's the blink of an eye. This presentation touched just a tiny part of rocket physics. This presentation is like touching the base of Olympus Mons. There is so much more. I hope that all of you enjoy this presentation, and you are free to ask any questions. Be gentle, I'm only 15. So any questions?
What spacecraft are using ion drive right now?
Well, I believe that
What spacecraft are currently using ion drives that you know of?
I believe that OSIRIS-REx and I forgot the name, but the mission that that collided with the asteroid a few months ago. Oh yes. There are a few others, but I forgot, unfortunately. Any other questions? Sorry, can you?
Sorry. I just wanted to say how impressed I was at your age, the quality of the presentation you gave. I can tell you at age 15, I could not have given such a great presentation. So thank you very much.
Thank you.
One more online question.
Okay, go ahead. Oh, you want the mic? Hang on just a second.
Would you like to travel to space, and where would you like to go if you were able to travel?
Well, I guess the next habitable planet that we discover, because why not?
Love the presentation. You dumbed it down enough for me to understand and follow. So I appreciate that. What do you want to do in the future when you grow up?
Well, I want to go into the field of cosmology, which studies the universe as a whole. Are there any other questions? I guess that's it.
All right, thank you very much, Lavi. You know, every time we run one of these meetings, I go through a standard set of 10 minutes of announcements, and in my welcome part of that, I say four things. I always say we hope you enjoy yourselves, and I hope you learn something new. And tonight I learned two new things I had never thought about until his presentation about the idea of escape velocity for the solar system. I've always thought about the escape velocity for Earth, and everybody kind of has a pretty good idea how fast that is because you see it all the time. But I never thought about having an escape velocity for the solar system, and the fact that it's 4 times higher than the escape velocity of Earth was fascinating to me. So I learned something new tonight. Thank you very much, sir. Okay, so perfect job. So our next presentation, before we have our short break and then get to our main presentation, is going to be from James Yoder here. And let me switch some things around here on the left.
So tonight I'm going to try to briefly kind of introduce you guys to an application called AstroPlanner. And what it does is it helps you plan your session out. Now you may wonder, why do I need a software to plan my session out? You can get books that have like best objects for small telescopes and stuff. But this application really lets you zoom in on any particular situation you want. It also is really good for exporting to different applications and stuff. So that's why I wanted to get the web browser up here. I wanted to show you a couple things. I've created a general list of interesting astronomical targets for our areas, for around the year. Wanted to show you where you could download that and look at it. So this is my website, and this is also where we host some of the EVAC information. Some of the EVAC links that Steve was showing you earlier come to this page or this website. So it's artcentrics.com, artcentrics.com. And before we get to the presentation, let me show you where the rental program and the purchase program's at. So if you just click on the EVAC page here are the list of items that we have for sale. These are obviously objects here. This is a list of some of the eyepieces that we've got going on here. As you can see, some of them are selling out rather quickly, so you might want to check that out. So anyway, that's just that page. Let me go back. And the rental program is right here also. I won't bother showing you guys that, but so that's that. Let me get back to the main directory there. Okay, so what I want to show you is one of the some of the files I created with this AstroPlanner. If you go to the main website here again and go under astronomy and scroll down, there's other resources. And here what I did was create a list of, like I said, objects that might be of interest to fairly small telescopes in this area. And you can see all the different list of items that are in this list. Using AstroPlanner, There's different formats that you can download. If you want to form the AstroPlanner application itself in that format, you can just click on this and it'll download that for you. We've got, I can't quite see what that is. Let me see if I can increase the size of that. Yeah. So we've got Sky Safari. If you use Sky Safari, if you click this link, you can download that file and import it into Sky Safari Pro. We also have an Excel spreadsheet that I exported out and a PDF, and I'll open that in a second here just to show you what it looks like. Just a note over here, the Sky Safari Pro only has 223 objects where these other ones have 260 because everything didn't export exactly out of the application properly. So again, we got like 59 carbon stars, double stars, triple stars, galaxies, open clusters, globular clusters, dark nebulae, emission nebulae, and planetary nebulae. So a whole list of things to look at. So again, you can download any of these formats. Let's just go ahead and look at the PDF format. So just click on that. And the way it's sorted out in the PDF is it's sorted by first constellation. So here's all the Andromeda, and then the type of object is listed here. The right ascension declination. This is the highest it gets in the sky when it's at peak during the season, 79 degrees above the horizon. The catalog associated with it, the ID of it, size if it's applicable, magnitude, and if it's a magnitude 2, that's like a multiple star system, separation from multiple star systems, surface brightness for the objects, and then other names that these objects may be known as, and then also comments. Some of these, obviously, some of these things I use different resources for, so some of them I'll just list what the resource was for that. Okay, so this is available for you. I've done a lot of that work for you, so you can just download this and use this list throughout the year. It's for all these different objects. So this is the output from the application I'm going to show you guys how to use. So let's go ahead and go into the presentation now at this point. Was that under? This one? Okay. Thank you. Okay. Let's go to the top. That's in the middle of the presentation. Okay. I'm going to increase the size of this a little bit. So the website for AstroPlanner is here. It costs $45. Again, it's compatible with Macintosh and Windows. Here are the requirements for it. Won't go into too much details on it. This presentation is many pages. I can't remember how many pages. We're not going to go over the detail of that. I'm just going to give you an idea of the functionality. But if you're interested in the full presentation, you're welcome to email me and I'll let you know about that. We're just going to go through some of the basic screens. I will tell you, when any of these programs that where you want to set up and for your system and everything, you're going to have to do a little footwork to begin with. You have to put in your instrument information, and it's a little bit of work, but it really pays off in the long run. And I'll show you closer to the end is where you'll see the real benefit of it. So let's just first dive into what the basic screen looks like. Oh, that's that. Okay, we just did that. So this is what the main screen looks like here in AstroPlanner. Hopefully you guys can see it okay. Up here, we've got the top ribbon bar. Oh, actually, above that, we've got the main menu bar up here where you have options up here. Then we've got the ribbon bar here, and we'll go into details of these coming below. And then instrument information, the time and location. You can see it based on where you're at. It'll tell you where the twilight is. And information like that. This is where objects are at in the sky when you have them selected in the list down here. We have the moon phase information. This is kind of a nice little graphic. It shows you when the moon is coming up and when the object that you have selected is up and how through the sky. And this is the yearly information about the objects where they are in the sky during the year. And then here's a nice little finder chart that has a constellation it's in. So you can see I've got this item selected here. Off to the left is the constellation. You can also download your own images, or you can select from surveys and see the image over here also. So that's the main screen. Going into more detail here. This is the menu that was up top here. Some of the stuff there, we won't go into details on that. There's a taskbar underneath there where you can do searches and stuff like that, observations. So yeah, we'll talk about that a little bit. And here's a widget bar. We've talked about some of the features here already. So this is the objects table. As you can see, you've got a number of columns up here. You can customize the columns to show whatever information you want. There's very many different things that you can put in here. And you can sort this list however you want it. And I mentioned earlier, when you have an object, if you'd like take an image of it, you can import the image into the application itself. And here is one of the pictures I took of one of these objects. So this is the main part of the screen, the objects table. And then there's actions you can take down here. You can add custom objects, remove, duplicate, find, and list preferences and so forth. There's also observations that you can do on it. We'll get to that screen, sort list. So there's a lot of things that you can do on it. As I mentioned just a second ago, you can log observations on individual objects, keep an astronomy log in here. And if you do, click on one of that and click make observations, you'll come up with this screen. You can put in what equipment that you use to observe it, any notes that you have, and your hardware configuration that you did it. This is a really nice feature also. It's the field of view screen. So like I said, you do need to do the footwork to put your equipment in there. And that's like, put your main scope in, your focal length and stuff like that. Here I've got the C11 selected and your eyepieces, or if you're imaging, you can put the imaging in there. And it'll actually, the view you see over here is actually going to be created so that it shows you what you should get for this hardware configuration over here. So you should see what you should see in your eyepiece. Now, it might not be as bright as it's shown in the picture because things generally aren't that way bright, but the size of the object that it would appear in your eyepiece is going to show up over here, provided you have the hardware information in there. So that's the field of view screen. I find it's quite useful to see what to expect when you're looking for something. The sky view screen is another thing. It's basically just the atlas, and it shows you where it is in the sky. Honestly, I hardly ever use this because it's just, this is the entire sky. So I don't really find a real big use for that myself. Maybe it's because I haven't used it a lot. The manual that comes with this is like 300 and something pages. So there's a lot of features on here. And for 45 bucks, it's a great deal. And this screen here is, okay, this is where you start putting in your hardware in and such. For instance, this is your observation site tab here where you put in where you're at, longitude, latitude, and that information. And these are the other configuration screens. Let me increase the size of that so you can see what they are. And we won't get into too much detail, but just so you can see the sites we talked about. Let me see. That's too big. Let me get it smaller. All right. There. Let's see if I can see what that says there. I think that's a telescope there, right? The telescopes, you can see you put information on your telescopes, and then you put information on your eyepieces here. You can even put filter information in there if you want. And what is that one? That's probably, I think that's the imaging stuff. I'm not positive. Can't see quite. Oh, focal reducer and hyperstar. Yes, different hardware, other different hardware. So this is the screens that you put that information. Here's the, if you have a camera, you can put the camera information in here and so forth. Anyway, so that's where you put the information. Again, it's a bit of work to put it in, but once you get it in, you get some really nice features on it. So for instance, on this screen, after you get the information in, you can see for this eyepiece and this telescope, I'm going to have this magnification. So it calculates all the magnifications for you automatically for any combinations of eyepieces and telescopes that you do. This table is generated after you put all that hardware in there. So it's just another tab and it's just there. So I'm almost out of time. So just real quickly, I'll show you how you could do a real world scenario. So for instance, if I was to observe in, let's say, southern Utah, and I wanted to do it, I could come in here and set parameters. I'll just do the one example. I could set the location, the date, the time, the telescope, the eyepieces I'm going to use. I would add planets because you can add planets and the sun and stuff, and then eliminate them based on how high or low the altitude is. And then I can go search catalogs, and I can actually put in there, you know, if I want the Messier list, I can search Messier list. There's a ton of catalogs that are here, multiple star system catalogs, NGC catalogs, all these catalogs are in here. And you've got all these parameters you can tweak in here. And, you know, you can say, I just want to check out this constellation, these type of objects, you know, and I want to do it at, you know, this date and time. So there's just a whole bunch of things at this magnitude, this surface brightness. You can put a lot of tweaks in there and get exactly what you're looking for. And that's the basic idea of it. Anyway, it allows you to customize to get exactly what you're looking for. It's a very powerful tool. So something you might want to consider in the future if you're looking to really streamline what you want to go out and make the best of your imaging sessions or viewing sessions, I should say. And that's it. Or questions?
You indicated you could sort on various fields. Can you sort on right ascension? Because that's real handy for telling you what time to look at it.
Absolutely, right ascension. And the sort allows you actually, the basic sort allows you to do 3 fields. So you can put constellation, right ascension, a magnitude. The other thing I didn't mention in here is there's user catalogs that you can download, and there's a ton of them. For instance, if you have a book, you know, a book that you're interested in, it's probably that list astronomical thing is probably in the catalog of things that you can download. So it's really cool.
Any other questions for James? So the question was, who maintains the application?
The developers of it, the catalogs, I mean, the user catalogs that you can download, you know, just users contribute to it. And I guess it goes to a database that you can download and stuff. And like I said, there are hundreds of different catalogs that you can do. So the users update that. The other catalogs are kind of static, like the Messier list doesn't change, right? But books and, you know, clubs and stuff like that upload stuff regularly here. Yep.
So Jeffrey Skype likes asks, does the purchase price include future updates?
You know, I think it does. I purchased it once and I haven't had to do any repurchasing, so I believe it does, but I can't say that for sure. It's pretty old school, I think, in that sense. You know, nowadays everyone wants to charge you a monthly fee. He hasn't gotten to that yet, at least. Thank heavens.
Any more questions? Because you just answered mine. I want to know if it's a one-time charge.
Yeah,
or
I
it's
hate
a
it.
or subscription.
Yeah, I hate the subscription thing.
Anything else, folks?
Okay, thank you.
All right, folks, we have our main presentation tonight is going to be given by Tom Mozdzen and Rick Scott, who's sitting right here in front of me. For those that are not in the room, they are going to be talking about a project they've been working on together. So I'm not quite sure which order they're going to go. I think Tom might be going first, but anyway, let's all sit down and let's see what Tom and Rick have to tell us tonight. Thank you. You just sit down there in your presentation.
Thanks. Good evening, everyone. I'm excited to tell you about the project Rick and I have been working on. I've been working on it maybe 4 years now, and it took me about 3.5 years before I felt comfortable enough to try and explain it to somebody else. So during the presentation, if you have questions, definitely ask. just so that you're not lost for the rest of it. See, I'm working half-time at Arizona State University as a assistant research scientist. And my job is to help grad students with their projects. And one of the projects I was on finished up, and another one came up, and it was intensity interferometry, which was Gena Pilavsky's main thesis project. And towards the end of it, he needed somebody to help him get his equipment on a telescope. And basically, the way intensity interferometry works is you have to detect two photons at the same time coming from a star. And they have to be the same frequency and the same polarization. And it's sort of coincidence counting. So I'll go into more detail later, but that's what you want to do. So you have to put a timestamp on a photon and from one telescope and a timestamp on another one, and go search through all your data to see which one, how often it happened at the same time. So what Gena did was he built a homemade timestamper because you couldn't buy one at the time. And so at the very end, there was like the summer of 2020, I was playing in the backyard trying to figure out, can you guide on a really bright star? Because, you know, if you use PhD2, it wants dim stars. And so I tried it with a Schmidt-Cassegrain and an alt-az mount. Everybody said you can't guide on an alt-az mount. I'm like, well, let me try. And it looked like it guided okay, but then I tried a polar mounting it instead of the alt-az mount. And that was a nightmare trying to get that thing polar aligned, you know, take a couple hours, and I didn't get any better results. And so I'm like, well, let's see who has a nice dome that might want to get interested in this. I'm like, hey, Rick, do you want to put some equipment on your telescope and see if we can measure diameter of stars? And, you know, Rick was like, sure, definitely, that'd be pretty cool. So that's how it got started. So let's see. So this is the prettiest picture we have in the whole deck. So that's, you know, spoiler alert. Yes. Do the telescopes have to be identical? That's a really good question. They should have the same optical delay through each of them, or else you run into trouble. So ideally, you want them to be as identical as possible. So yeah, I'll try and repeat questions that come up, and definitely ask questions. Like I said earlier. So I guess one question is, does everybody know what a airy diffraction disk is? When you you know, look through your telescope and you defocus it a little bit, you get different rings in there. I mean, there's some head nods, some not. Okay, and that photons are sometimes considered waves and sometimes are considered particles. Yeah, so we'll get into that pretty heavy pretty soon. But anyway, let's start. So why do we do this? Well, the grad students needed help and a telescope, and I like the weirdness of photons. They do really weird stuff. You know, they travel at the speed of light. So does that mean time stands still for them? How do they experience things? And they can make interference patterns going around some structure, even if only one of them goes through at a time. So it's like, what? How? Somehow it sees both of them. And so, you know, that's definitely weird. And this intensity interferometry thing sounded really interesting because I thought, okay, this is a good chance to learn some more about photons. And Rick, I think you used similar, interesting and different astronomy project that you could do with your backyard observatory, put it to some good use, and measuring angular diameter of stars. How cool can that be, you know, from your backyard? And both of us like working with grad students and being around young people and, you know, helping them out. Because the grad students are under a lot of stress. You know, it's a tough time of their life. They're in their mid-20s. and they're spending 5 or 6 years on a project that may or may not work, and they're going to get a job in this field, and they may or may not like that job. So it's like it's very stressful mentally for them. So any help a seasoned veteran like Rick and I could give them, they definitely appreciate it. Okay, so the talk outline is the background theory. We're going to start with a Michelson stellar interferometer and show how that's different from an intensity interferometer. It's kind of like the yin and the yang. You know, you don't know how good chocolate is until you've tasted vanilla, or you know, you don't know what good is until you know bad. It's so, yes, Tal. Are the interferometers on Mount Wilson Michelson's? I think the answer is yes. I'm not, yeah, I think we have, that's your picture of it later on, right? Yeah, amplitude interferometry. So we'll go through the theory a little bit. And then part 2, Rick will talk about the equipment. And then I'll go back on and talk about our results and future plans. Let's see. Okay, just briefly here, well, we'll start with the Michelson stellar interferometer. So what they do is they take 2 mirrors and they reflect it off the telescope and combine the light, and then they measure that combined light. So those waves are interfering, and you have these little 2 mirrors that are picking off points of light from the star. And you can see this one is pointing at the zenith, and this is the distance d between these mirrors. It's often called the baseline. In an intensity interferometer, you measure with each scope individually, and then you combine them later. So you measure, and so you don't measure wave interference. You measure correlation. I'll try not to say the words correlation or many equations, because if we start getting into correlation, then it's going to take 3.5 years to get all that straight. Anyway, so I'll bring this diagram back up later. So the background and theory for Michelson stellar, it's been around a long time, 1800s to 1900s. I think people are still doing it today, like in Flagstaff, there's the Navy precision optical interferometer, where I think the Navy was paying Lowell to take care of it and work it. And Lowell was like, you guys aren't paying us enough money. You know, here, take it back. And they took it back. And I think the Navy realized, okay, yeah, we should pay them some more money. This is not easy. So again, you place the 2 mirrors a certain distance apart. You combine the light waves, and then you measure the visibility of the interference fringes. And I'll show you in a little bit what exactly we mean by the interference fringes and visibility. Okay, and that's the signal you measure with the interferometer. And so you repeat this and you move the mirrors further apart, and you further apart. And then when the fringe visibility finally goes to 0, then that distance that those mirrors are separated by gives you the angular diameter of the source. So once again, the visibility, the fringes is the signal you measure, and these are the fringes, these patterns of light and dark areas. And a weak fringe would be where the dark part starts to get light, and the light part isn't quite so bright. So when that starts to fade, that's when you say the fringes went away. So for the intensity interferometer, the measuring devices are also placed a certain distance apart. And you measure the light intensity at 2 points. Don't combine the light. Then you figure out the correlation of the intensity fluctuations, either wave-based or photon counting based. Two photons arriving nearly simultaneously is the signal you measure. You do get a lot of noise, and so you have to measure a long time. And then you repeat with the mirrors further apart, and then that signal gets lower and lower. And again, when it finally goes away, then you know that's the baseline, and you get your what the 1.22 lambda over d is your angle. So yeah, so once again, the visibility of the fringes in the Michelson interferometer and 2 photons arriving simultaneously is for intensity interferometry. Yes, Steve.
Would it be, that's my question. Is it like 2 photons out of 1 billion, 2 photons out of 10 billion, 2 photons out of 100? I mean, you said there's a lot of data. So.
Yes, the question is, how many photons do you get out of, how many signal photons do you get out of the background photon? Let's see, what, I'm going to swag it. Maybe, what would you say, Rick, 1 out of 1 billion or something like that? Yeah, they're fairly small. So when we get to the graphs, I'll be able to, I've got some numbers there. I think it's like, well, at least less than 1 out of 1,000. But yeah, good question. How many? So yeah, we had to integrate at least 5 hours to start to see a signal, and we were getting 4 million photons per second. So it's like, yes, tell.
Like, does this seeing have anything to do with this? In other words, do you need seeing, or does it matter?
Yeah, so the question was, how does the seeing affect this? So has the 2 possible ways to affect it. One is to change your optical path and make it not come in at the same time. You know, if they were coming at you at the same time, if one hit a pocket of seeing that the other didn't, that could throw it off a little bit. That's not as bad of a problem because it's a short distance. The other problem would be if it interferes with your guiding and the photon falls off the fiber, because we have to hit 100 micron fiber to get the photons in there, which, you know, on the surface doesn't sound too bad. You know, maybe it's plus or minus 4 or 5 pixels, something like that. But it's I guess easier said than done, because you do want it centered, because we do have a detector that likes to get the photons right in the center of the detector. So we'll show you some examples of what happens when you're not exactly centered. Okay, and let's see, yeah, as you mentioned, Mount Wilson. Here's, and there's the 2 mirrors that they use to pick off the light. And they put it on a bar so that when you point it at the star, both mirrors are still perpendicular to the incoming direction of the light. And so that makes it easier, as opposed to having 2 telescopes on the ground and you just tilt them, and now one has a longer optical path, and then you have to compensate for that. So just a little bit with interference. If you look at it, treat it as a wave, you get destructive interference when one's at a peak and the other's at a minimum. You know, positive and negative, they kind of destroy each other and you don't get light. And then when they're both in phase, sometimes we call that they're coherent. Then you get a bright fringe, and here's another example. So this two slit experiment or demonstration is sort of like the interferometer, because you get light waves from the star that they're plane waves, they're like big pancakes coming at your telescopes. And when they hit these 2 openings, the light spreads out, and the one from one slit interferes with the other slit. And so, you know, you get these concentric waves. And if you look at a screen, you see that you get bright and dark spots. So those are, so that's the fringe pattern. Okay, just reinforce the wave nature of light. So, yeah, question from James, yes. Oh, from the Zoom people.
Yeah, is intensity interferometry used in the very large array in New Mexico?
Oh, is intensity interferometry used in VLA? Right now, we don't think anybody is really using intensity interferometry. Some people have tried with larger scopes and they do a short, I don't know, year and a half observing session, and then they give it up. But yeah, I don't know of any active right now. Do you, Rick? Do you know of any that are?
Small groups like us, France or Italy.
Yeah, just small groups like us. We, yeah. Oh, question. Yeah, VLA is more like there's a lot of interferometric arrays out there that are multiple telescopes, but that's a little bit different. They're actually imaging the sky with this. It's like a gigantic telescope with all the pieces chunked out, except these antennas in an array. And that's much more complicated. So Nathan, your question?
Why does the size of the scope matter if you're collecting 100 microns?
Or why does the size of the telescope matter if you're squeezing it down to a 100 micron optic fiber? Well, you get a higher count rate. You collect more photons, and so you don't have to wait as long for that magical pair that are, you know, identical. Let's see, for the yes, you're shoving all that light into that fiber. Yeah, and yeah, and our detectors can only go up to maybe 3 or 4 million photons per second because they have dead times of about 80 nanoseconds. After they detect the photon, they have to recover, and then there's a dead time. Yeah, Tal, yes.
Does it help to filter, like looking for like big diodes and alpha line?
Yeah, excellent point. Because on the bench, we do H alpha. We use an H alpha source, but yeah, we have it's a double-edged sword on the telescopes because it does help make your signal spike narrower and more well-defined, but it also reduces your count rate. So you still have to integrate the same amount of time. It's just your, I think your count rate gets a little bit sharper, and that would also let you use a larger telescope too. If you had a larger telescope, then you can take advantage of a narrower filter. Because if you have too large of a telescope, then there's too many photons for your detectors. And so if you did have a narrower filter, then that would help both ways. Okay, another one. This is good, yeah.
Your talk, turn it into a Q&A session. Are you gonna have time to do the talk?
Yeah, we'll get there. Well, this is good you're asking these questions because a lot of these things are covered in the next slides. And like one of my teachers said, what's learning other than seeing something for the second time? So we'll get to see it for the second time. There's so many wonderful educational YouTube videos out there by people talking about optics and physics and all sorts of things. This guy from France, Frantz Martinache or Martinache, he has a wonderful talk here, and I've shamelessly borrowed the next 10 slides from screen captures of his talk that illustrate a lot of things. So if you see the black background, I did give him credit on the bottom, but just, you know, if you want to go and look at the whole thing yourself at another time. So yeah, this is just to say that the first attempt was in 1873. He wasn't successful. That's a that's a gigantic telescope. Yeah, he had trouble controlling the distances, and so okay, so put that one to the history books. So we can think of it as masking a telescope. So if you don't mask a telescope, here you are with the diameter d for your scope, and you have a faraway star sending out plane waves, and the intensity of the light that you see is a spike with some ripples, and we call that an Airy pattern. And from the top, it looks like that. It just means most of the photons arrive in here, and then you have some dark areas, and then light areas, and dark areas, light areas, and actually, when you talk about resolution, if you can split two stars, if you were looking at two stars, they'd each make one of these patterns, and you move them together until these two bright spots start to overlap, and then you can say that's the resolution of your system, is when those airy disks overlap. But that's a side topic. Anyway, yeah, we get 1.22 lambda over d is that angle you get from just one telescope. So let's say you cut a hole in a plate, you bounce the, instead of sending it here, is put a 45-degree plate and you send it through something that has a smaller diameter hole d, so it's like stopping down your telescope. And if you look at that pattern, it's a big fat pattern. So you lost resolution because your opening is quite small. And now if you have two patterns like that, or two holes like that, now you get two of these patterns overlapping. And you can see you start to get fringes there. Yeah, you can actually beat the typical resolution curve of 1.22. You could cut it in half or by a third with a technique like that. You lose a lot of light and detail, but that's one way to beat the equation. So now if you have a star that is resolvable, that means like you can tell the left part from the right part, and maybe it looks like two stars. So you would get these patterns here. Each one of them would have their own pattern and they wouldn't exactly overlap. And so if you brought those together, use two telescopes to do that instead of the two mirrors, you brought them together, you get a pattern like that in the middle. And as you move the telescopes further apart, so you have well-defined fringes here, and then you go here and they start to disappear and you move it further away and they're almost gone. So that's the sort of the fringe equation. And the visibility is just defined by the like the maximum of the peak minus the minimum of the peak divided by the sum of the peaks. So when you do Michelson interferometry, that's what you're looking at. You're looking at that visibility of the fringe pattern. And yeah, and the theta is the 1.22 times the baseline at which it goes to 0 divided by the wavelength. Okay, so that's confusing enough how an amplitude based. Yes, question. Mm-hmm. Yeah, the question is, does this imply that you're looking at monochromatic one wavelength light? And the answer is yes. Yeah, so you need filters in there to get rid of the confusion of the other wavelengths. Okay, so intensity interferometry. This was proposed by a gentleman named Robert Hanbury Brown. And unfortunately, His last name is Hanbury Brown, which leads to a lot of confusion. Is his last name Brown or is it Robert H. Brown? But he goes by Hanbury Brown. Anyway, he was a World War II radar expert, and after the war, he turned his talents to more academic pursuits. And in 1949, he was tasked with measuring the diameter of radio objects in the sky. And he thought there has to be a better way to do it than with the Michelson interferometer. You know, why don't maybe the intensity at 2 points, maybe there's some relationship there between them. And so he gave that a try. And he teamed up with R.Q. Twist, who had a better math grounding than himself. And they put it to the test. They did some work in a bench to show that they could see a spike. And they did this with, I think at first RF frequencies, and then they moved it to optical. Oh yeah, they had success doing this in maybe sub-millimeter range with gigantic telescopes. And then they said, oh, we got results, but they weren't as good as what people were getting with other telescopes. Like, what's the use here? But then they thought, oh, if we move this to optical, this would be much better if we did it in the optical range. Anyway, so when they published these results, this caused, well, like one person said, if threw the fox in with the pigeons, you know, just created just a giant amount of debates, and you know, you're wrong, you don't know what you're doing, and other people are like, oh, wait a minute, I think they do. And so for about 2 years, they went back and forth with papers saying, no, we tried this technique and we got nothing. And then Hanbury Brown and Twiss would say, well, yeah, that's because this thing you didn't have enough precision in this area. And then some mathematicians came to their defense and showed, yeah, you should get a spike. And after about 2 years of this, it kind of calmed down and like, okay, yeah, this is real. And here's some mathematical backing for it. And yeah, the physics community went back and forth like, oh, it's, you know, is it a particle? Is it a wave? And they were mixing up particles and waves together. And people were saying, no, if you're going to look at it as a wave, stay as a wave. If you're going to do particles, stay as a particle. And in the end, yeah, they were correct both in experiment and theory. And 1953, Roy Glauber, is that 53? No, 63. Yeah, Roy Glauber developed the quantum theory of light that put this on really solid fundamental theoretical backing. And 2005, he got the Nobel Prize for it. And unfortunately, Hanbury Brown was dead by that time, and you don't get to be on a Nobel Prize if you're dead. So he kind of missed out. But people suspect you'd probably be awarded it. Okay, so let's see. We're going the particle view of the photon. One reason why is this being why are people interested in it today? It's because the electronics have improved so much. We have very accurate single photon detectors with very little jitter. You know, they'll give you, they get a photon of light, they'll send you an electrical signal, and the timing on that signal may have a jitter of maybe 40 picoseconds or something, which, you know, that's really fast. Or that's a low number. And time stampers, you give an electrical signal and the time stampers will give you a time of when this photon arrived to what we're maybe tens of picoseconds. Anyway, okay, so how do we do this? We point 2 telescopes at a star. Each has a single photon detector. And the intensity is a number of photons per second, or a count rate. You know, how many photons are you getting? And again, this is single frequency. And it should be single polarization, but that's too much trouble. You have to integrate longer, but it'd be too hard to keep the polarization filters in the same direction for the whole time. Okay, so you send the output of detectors to a time stamping device. So right now we're using a time tagger Ultra by a company called Swabian. And they were, you know, like I said earlier, Agena had developed an electronic Roach board or a board, BG, what's it called? The programmable FPGA board, where he could tag a photon with a time of maybe, I don't know, plus or minus 300 or 400 picoseconds. But in the meantime, a commercially available time tagger was available, and they were really nice to us. We didn't have money to buy it. It was about $13,000. And they said, here, try it out. We'll send it to you, you know. So for about 9 months, we were using it. So finally, we got some money and we were able to buy it. So great. So we're happy.
Tom, how did you get picoseconds accuracy on a computer system with nanosecond accuracy clock?
Nanosecond accuracy.
Picosecond
Oh,
accuracy
did
on a
I
computer with the system with nanosecond.
Oh, maybe, I don't know. Did I say nanosecond earlier? How do I get picosecond accuracy on this time tagger?
Yeah, if the clock is, it says, how do you get picosecond
Okay.
accuracy on a computer with a clock that's nanosecond?
Oh, okay. So this is a standalone electronic device. You know, Rick will show you the device in a little bit. Yeah, the timestamps are sent to the computer via USB cable, and that's only at like a 5 megahertz rate, something like that. So it can easily handle that. Yeah, tens of picoseconds. That's amazing. Okay, we're using the particle view. We process the data by how long it took for a photon to appear in scope 2 after or before a photon appears in scope 1. So we're looking for simultaneous data arrivals. So you have to you get a big stream of data, and you look at when something happened on channel 2, how far before it did it happen on channel 1? And if channel 1 got a photon before channel 2, you measure that time. You know, how long was that? So this one's like, what, maybe 40 minus 40 picoseconds. So it goes, you increment that bin. And this one is what, about 60 some picoseconds after the channel 1 hit, and it goes there. You know, if they're simultaneous, it goes there, you know, minus 100, you increment that, and you build up a histogram like this. So after we have all this data, we can analyze it at our leisure the next day. And the strength of that coherence spike is one data point of several needed to trace out the curve. So here's that Airy function for the Michelson interferometer. It's this curve that goes negative and positive. And for the intensity interferometer, it's that curve squared, you know, multiplied by itself. So it's a little bit steeper, and their zeros are the same. So they are a bit related. Now for the star Sirius, in Rick's backyard, we have them 3.3 meters apart. So we're getting close to the point of the maximum signal in there. So when they're right on top of each other, we'll get the full strength of the signal. And as you move them apart, that signal is going to get weaker and weaker. So that's one baseline. Then we have another baseline out here waiting for us to put a telescope on it. And once Sirius comes up again, and that's 10 meters away. So if we got 2 points there, that would be nice. That would say we're kind of on track. So that's the goal. Maybe we'd measure a third one at 15. Hard to say. So yeah, so you repeat that the data collection with the telescopes at different separations, and you measure enough points so you can extrapolate to 0. And again, the angular diameter is 1.22 times the baseline over the wavelength, that airy formula again. And so here's the secret sauce. This was probably the hardest part for me to get in my head. So there's different types of randomness or variability in random things, put it that way. So this first one is, they call it anti-bunched. I don't know exactly how you make something come out that has less variation. I don't know. No, laser is this one. Laser is the Poisson. So this, yeah, so I don't know if so it's less regular than I mean, it's more controlled than a laser. Laser has constant power. So this doesn't work with a laser. This is like a Poisson distribution, which is like if you flip 10 coins, how often do you get only one coin come up heads? So it's where the probability of that state is very low. It's close to 0. So if you have something with thermal light that's caused from a black body, something in thermal equilibrium, and these come out more bunched than a random, than the randomness of, say, a laser. And because they come out in a bunch like this, you can get some of them coming out nearly simultaneously. And if you do the math, you can show what the correlation or coherence of those two are. It's like how often does that happen? And so that's, like I said, that's the secret sauce. That's just how thermal light is. And if you go through all the statistics, that it comes out that way. So in the beginning, I'm like, why are they bunched? Why do you say bunching? Is it just random or not random? And it's like, it's super random, or it's bunched random. Anyway, so the other thing we have to worry about are baselines. You can see when these two telescopes are pointing at something on the horizon, the angular separation of that light coming in is at a shorter distance than if it were looking straight up at the zenith. So you have to take care of that. And here's an extra time delay for this one. So in a Michelson interferometer, if you wanted to null out that time, you would have to intercept the short one and send it through a maze of mirrors to add some extra optical time so that they'd actually arrive at the same time. So you want to cancel that out. So that's pretty tough in a Michelson interferometer. Yes, Nathan.
So how can you say that they arrive at the same time?
Mm-hmm.
Does that mean that they're necessarily source?
No, here's the other screwy thing. It's required that they know nothing about each other originating on the sun. They have to be coming from different spots on the sun, and they just have, or a star rather, and it's important that they are random from each other. And by the time it gets to say the Earth, they're spatially coherent. People say, like, if you throw a bunch of rocks into a pond and you look far away from this where you dropped all those rocks, you just see one nice smooth wavefront coming in. And that's just because you're looking at such a narrow view of the star, and it's looking as a point. And so that's why they line up. But yeah, so you're looking to see if they if your telescopes are pointed in a 90 degrees face on to the source, the ones that are arriving simultaneously in that situation are the ones that you want to use. Yeah, wavelength. Yeah, wavelength. So we have a 1 nanometer filter that we filter out the light. Yeah, and for Sirius, we get about 2 million photons per second per telescopes, and Vega, it's about 500, right, with the new detectors. Yeah, we had another problem with detectors where one of them broke, and again we went begging. We found a company that said, "Oh, here, try our photon detectors. They're great. You know, you love them." And same thing, we didn't have money for about 6 months. They're like, "You guys gonna buy these or not?" So yeah, we're working on it. So we finally bought those. Anyway, I should hurry up here. Okay, so yeah, back to how it works. I'm almost ready to hand over to Rick. So yeah, you measure, store it on a computer, and go home. Digitally add any extra delay you need to on that thing. It's a very complicated equation, believe me. A lot of sine and cosine terms with your latitude, the star's declination, and the hour angle that you're observing at. Okay, so and this is one where we had a beam splitter. Yeah, Rick will tell you about how we were doing guiding, but one telescope had more astigmatism in the star image it was trying to guide off. So, you know, you get dropouts and then you get fuzzy. Sometimes we'd have to adjust it by hand. And here you can see the star was starting to set at night, and we're starting to get a fall off from extinction in the sky. And so let's see, so for 3 hours of data, you get 160 gigabytes. And so you do, you know, if you get, I don't know, 15 hours of data like that, you're getting close to a terabyte. Oh, so yeah, so on the right here is this is the simple thing we get analyzed. You get a timestamp and the scope number. You know, there's scope 2, scope 1. Nope, that's too far apart. Skip it, too far apart. You get, and we were just looking for plus or minus 400 nanoseconds. If it's more than that, we stop looking. Okay, once again, that center thing is what we're looking for. And that was hard to find. Okay, so Rick, take it away.
So when I first got involved with the project, they've been doing work in the lab for 5 years, 6 years or something like that. And I had telescopes available, I had mounts and stuff like that. So we finally got on the sky. And so basically the equipment you need here is you need to have 2 telescopes at least. You can do it with more than 2 telescopes, but it gets more complicated. And we're just learning how to do this right now, obviously. You need to have 2 optical systems that are used to focus and filter the light onto a fiber optic cable. Then you have the fiber optic cables that feed the single photon detectors, and the time tagging device, which Tom has mentioned a few times, and the computers for doing the analysis of the data, running the guiding software, running the time tagger. And then for indoor testing, which we are doing currently right now, we have an optical bench, for testing the system, calibrating it, because like we're getting to the monsoon season, lots of clouds, so we go in the lab. So this is in my backyard, and you can see the 2 scopes there set up on 2 different baselines. The closer one is the 3.3 meter, and the farther one is temporarily was on a tripod. Now we have a permanent pure foundation that we just put in a few weeks ago, so we can have a more stable location for that, and that's the 10-meter location. And one of the factors we need to know is exactly what is the baseline between the telescopes. So a couple of weeks ago, we got some surveyors that come out for free and survey the place for us, from Chase Systems, I think was the name of the place. And these guys are great. I learned a lot watching them about how they do the, the surveying and measuring the distances. This is really a cool thing to watch. So here, one of the things you got to do is you got to guide in the star. You're trying to, stare at a star for hours on end. And originally we were doing what most astrophotographers do. We had a separate guide scope piggybacked on the main scope that you're imaging through. And you can see in the orange curve, it shows you what would happen after 20 minutes or 30 minutes. It would drift enough because of differential flexure, it's mechanical flexure in the system. And the light would fall off the fiber optic cable, and we'd have to recenter it. In the blue curve, we designed and built into our optical system a built-in on-axis guider. We're actually guiding on the star that we're actually feeding into the fiber. And that's a 3-hour plot, and it just sails right through beautifully. For astrophotography, if you're only doing 30-second or 5-minute exposures, obviously the piggyback approach works okay, but not for 3 hours at a time or more. Actually, one night we did 5 hours and it just worked beautiful. You can see it drop off due to atmospheric extinction. So this is what the optical system looks like. And the light comes in, from the left, and you see where the telescope focuses, and that's normally where you would also place an eyepiece. So the first lens here would be where like an eyepiece would be placed for your eye. And it just collimates the light, which is what your eye wants to see. It's also what the filter wants to see. If you have a cone of light going to filter, it's going to shift its center frequency and widen its bandpass, and we don't want to do that. We want to get the narrowest bandpass we can out of the filter. But in front of the filter, I have a beam splitter that directs light out to a lens in the camera, so we could use that for guiding and seeing where the star is when we're doing initial centering and focusing. And then the light passes straight through the beam splitter and goes to the filter. And then we have another lens that focuses it onto the fiber optic cable. And the beam splitter sends 10% of the light to the camera. We want as much light as we can into our single photon detector. And we're doing bright stars. So even with only 10% going to the camera, we still have to put a neutral density filter in there. It's too bright for the camera and saturates it. So one of the things we need to know is, well, how good are our filters? We buy filters and you can, you need 2 that are matched. So we found some people at ASU that had a spectrophotometer that we were able to use, and we measured the filters, and you can see they were actually pretty good. They just a little bit of non-overlap between them. So each one's like 1.2 nanometers wide, but we're getting an overlap of 1.1 nanometers, which is really great. Narrower would be better, but those filters get expensive and they don't track well over temperature. So the optical system we call Jazz Eye. It's named after my observatory is the Jazz Observatory, and these guys in Italy had a system they called the Aqua Eye. So I said, oh, okay, we'll just call it the Jazz Eye. So the very first version is as simple as you could possibly get. It just had the 2 lenses with the filter between them. And when we got on the telescope, we realized that trying to aim the scope accurately to keep the star on the fiber was really difficult for initial centering. So we added this device with micrometers that you can do really fine motions to center the star on the fiber. So that's what we started with. And then we would either, this one shows the fiber on it, we would put a camera there, and then we'd swap it out for the fiber, and we found that was a pain. So eventually we added a beam splitter and the camera to be a permanent part of it. And our first beam splitter was this thing called a dichroic mirror that reflects the light in one band of wavelengths and transmits through a different band of wavelengths. And so that was pretty cool because we can get almost 100% transmission into our fiber and almost 100% into the camera, but at different wavelength bands. But as we found out later on that we had some astigmatism issues. So the picture on the very right shows the prism that we've replaced the dichroic mirror with. So this is, I don't know if you guys are familiar with the PhD2. This is common guiding software when you're doing astrophotography. And so here you can see what the star looked like with all that astigmatism. So this is in PhD2, this is on the sky, and this is using our simulated star in the lab. So it's a much cleaner, sharper image because you don't have to deal with all the seeing effects of the sky. And then same thing with the prism, nice round star. PhD2 works a lot better with a a nice symmetrical object to find the centroid for your centering. So this shows our old time tagger over, not time tagger, photon detector here, which these guys were using when I first started with them. And this is some initial testing I was doing, when I was first getting involved with the project. And then, a few years later, that one died. We got some new ones. So this is the new detector. That's right now. This one is strapped to my pier in my observatory. And it's a much better detector. It was really a good thing that the old one failed. It cost us a bunch of money, but this thing works way better. So it's just a little box. It's only about this big. And puts out a digital pulse for each photon it detects. And so Tom mentioned that the student-built time tagger is this little box that's underneath here. And it wasn't so little, actually. It was about this big square. And it didn't really work that well. It was a pain in the butt to use. But we suffered with that for a while until we, got the new time tagger. If I can find the mouse cursor again. This thing's much smaller, much more capable than the one we had been using. And this allows us to do things in real time on the screen that we could not do with the other one. The other one, you sort of cross your fingers, hope you're getting good data until you analyze it. Here, we can see some of the data in real time. So here's what the setup looks like on the optical bench, at least the business end of it. At the far end of this is our light source. And what we're doing, we take a, well, I think the next slide will be better. But you can see the two jazz eyes on there with the cameras hanging off of them. But this shows you what's going on in the light bench. Everything to the right of this dashed line is the same thing we put on the telescopes. So the stuff to the left of this is what's on the optical bench. And we have a hydrogen alpha lamp. We focus it into a small pinhole. It's like 12.5 microns in diameter. And then we take the light from that expands like starlight would, and we focus it so it's a collimated beam. We could put filters here, we could put attenuators here. There's different things we could put here depending on what tests we're doing. And then we have another lens that focuses into a beam splitter that splits it off, and that sort of simulates it, the starlight going into two different telescopes. And the rest of the system is the same that we use on the telescopes. So there's a lot of advantages to this. You don't have to worry about stuff moving in the sky. You don't have to worry about seeing effects, but you're not measuring real stars. But at least it gets us to test the system and make sure it's all working right. I guess that's my part. It's fun stuff.
Okay, we're almost done here. So the old SPAD data will show what we get on the bench. So yeah, after Genna graduated, another grad student took over. His name was Todd, and he was able to take the project a step further and actually show a correlation spike. This was on a lab with a kind of a screwy hydrogen alpha source that I think Rick identified that there were some oscillations in there, and this is why the counts were going up like that. If we extended it further, this would be sinusoidal, but we did see a peak there, and that's what Todd had to work with. Then with the new system, we get a much more distinct spike there at the H alpha spike. So that was really a wow. I think we saw that after the sky stuff, didn't we? Or I think we did the sky and then we went back to see. Yeah. So this was the results with the lower resolution SPADs with, I don't know, several hours of data on Vega, and we're like, oh God, is that a signal? Is that something? It's like, oh man. And we tried an artificial thermal light source on the bench, and we couldn't see anything. And we're like, oh, we're going nowhere fast if we can't see this basic signal. And so, okay, so Sirius, that's the brightest star. We've got a shot with Sirius, and let's give it a shot. So the next 12 slides show the growth of the signal in about hour increments. So, yeah, so after a night of observing, I analyzed the whole 4 hours, but thought it'd be nice to see what was happening hour by hour. So there's the first hour, it's like, yeah, nothing. Second hour, nothing. Third hour, maybe something, because we had an artificial 200 nanosecond cable delaying things, pushing things off. And then let's see, then the last part of it, like, oops. So this is from our first data set, like we might have a signal here, like we're guardedly optimistic. And the next hour, second night, it's still there. It's getting a little bit stronger. And then next night, I think there's one more. Yeah, it's like, that's definitely a signal. So that's, we said we'd have a glass of champagne when we got that, but we still owe ourselves that glass. Yeah, and then Rick threw another slide in here showing the full range from like minus 400 nanoseconds to plus 400 nanoseconds. This is the whole range we looked over, and you can see there's some noise over here. That's why we shifted it. But there's our signal. That's like shooting up like the Empire State Building back in the day. So that was that. And future plans, larger telescopes, maybe more baseline simultaneously, or a spectrometer cut up. You know, why only use one wavelength band? If you could break it up into 3 or 4 wavelength bands, then you can get 3 or 4 times the data in one night. And then maybe measure more exotic objects like a quasar or a BE star that has some sort of hydrogen accretion disk, or it's emitting H alpha. Okay, yeah, and you need larger telescopes because they're dim. So that's it. Thank you for your patience. Oh, okay. Rick wants me to go back to this one.
So one thing I want to say about this is one baseline. So when we go to the farther baselines, that spike will diminish in amplitude. And that's what we're going to plot along those curves to eventually extrapolate to, the angular diameter of the star.
Question? Yeah. Oh, the star? Oh, the angular diameter of the star, or the baseline? How far back? Like this one, or? Oh, the polarization. Yeah, these photons are supposed to be in the same quantum state. So if you get one polarization one way and the other is 90 polarization, they don't count for a signal. So you get some false signals that you have to throw out. Oh, right, yeah. We'd get a lower count rate because we'd throw out half of the counts, and but the amount of false alarms would be lower also. So yeah, it's kind of
Factor 2 in the visibility equation.
yeah, but you have to integrate longer, right? Because your count rate is lower, but
But we're not doing that yet. Eventually, we may do the polarizers, but then we got to figure out how do you make sure that they're exactly the same direction. I mean, it's off a little bit, you just lose a little bit of signal, and then you got to maintain that while you're tracking.
so I think Tal asked, your name's Tal, right? I forget. I don't know. The question was asked earlier, do the telescopes have to be identical? And it does help to make them be identical, because you have to calculate the optical path delay that you're adding all the time. And turned out our 2 telescopes were I think the tube was 1 inch further off in one direction and another part of the mount was another inch longer. So we may try and put some spacers in there to make them more equal.
And people have done this with very dissimilar telescopes, but it's a lot more work to get the data.
You're trying to do this with small telescopes. I suppose, but I don't. Has anybody measured the diameter of stars?
Oh, yeah. So yeah, these are well known. Hanbury Brown and Twiss, I think they measured maybe a dozen stars like this. And so I estimated our count rate based on what the radius was and how far away it was. Oh, so you have to know the distance also to know the radius, because we're just getting the angular diameter. So some other way you have to figure out.
You've got a star, you're trying to get photons from different places around edges of the star.
No, they're just coming in randomly. Yeah, so if you do the wave nature of it, they're coming in and the frequencies aren't identical and you get a beat frequency that's like lower. And that beat wave is also coherent as it hits both telescopes. So, it's difficult to think about what's going on there. Yeah.
Question.
Yes.
Did you place scopes along west, east, or north-south directions?
Oh, yes. We tried to keep it just straight east-west, but Rick's wife would be upset if we chopped up a sidewalk in the backyard.
It can be done either way. You just have to use these equations to calculate the baseline change.
Yeah, just for fear of getting too far into the weeds. Oh, what happened? Did it close?
I just depresent. Should go back up on the screen. There you go.
Oh, no. Oh yeah, Rick's neighbor said, if we pay him some money, then he'll let us trim his tree. But yeah, there's, optical path delay zeros the zenith, and this is to the west. No, I'm sorry, that's to the east, and that's to the west, and this one here, that's Vega, and minus 16.7. That's Sirius. So I have to, every 15 seconds I have to adjust the time corrections. Yes, one more. Probably, I think we're going for monthly notices, Royal Astronomy Society, and then RAS. Probably there. That'll be our first shot. Yeah, thanks. And let's see, what's the other one? Oh yeah, I don't want to talk about that. That's too confusing.
Another question.
Okay.
Do you have to worry about Doppler shift? You're doing a very fine wavelength.
No, 'cause we're not actually interfering the light. We're just, time tagging the photon arrivals. We don't have to deal with any Doppler shifts.
Okay.
But yeah, I think the Doppler shift on the star would be low enough. Not to, that's probably a little bit of a smear in the.
They're close enough stars is what you're saying. That you don't have to worry about Doppler.
Oh, you mean the star shift moving away from us?
Or to get, yeah.
Yeah, no, because it'd be the same for all of those photons.
The wavelength we're using is dependent upon the filter, right? So whatever, if the star is redshift a little bit, doesn't matter. We'll just be looking at a different part of this black body radiation curve.
Right.
It'll be the same for whatever, for all the measurements we're taking.
Okay, thank you, everyone. You were very patient.
Well, as you can see, that's all, folks. So anyway, we are done for the night. Thank you very much.